Good afternoon, everyone. This is quite gratifying. When they published the schedule, and I saw that I was up against Kevlin, I thought I might have like 4 people in this room. But apparently, algorithms is an exciting topic to many people, and that's great. My name is Marshall Clow. I work at Qualcomm. I maintain the LLVM standard library implementation, libc++, and I'm also the chair of the library working group at the C++ Standards Committee. I've been writing C++ for a long time and contributing to Boost and various other places. And I want to talk today about STL algorithms, and in particular, how to write your own, because there's really nothing magic about them. Before we start, I have a disclaimer. There's a lot of code on these slides. And every single bit of it worked before I put it on the slide. and then I started fiddling with it to make it look a little nicer or to make it fit on the slide or so on. And I may have introduced errors at that point, but it worked once. Also, if you have any questions during the presentation, please put your hand up and I'll try to answer it right away. I'd rather not save questions till the end where they might get forgotten or lost. It's possible that you will ask a question that I'll say, just hold on to it because I have a slide coming up about it. But otherwise, I'll try to answer it immediately. OK. Operator failure. You have to turn the thing on for it to work. So we're going to start off with a very, very quick, very high-level overview of the C++ standard library, and we'll talk about where what I'm going to talk about today fits in. The standard library you can think of as being part of, it's basically broken into 4 things. Containers. Containers are things like vector and list and deck and map and unordered set and things like that. These are the things that people really get started with when they use the standard library. They're very convenient. They're well understood, they're well specified, they're much easier than writing your own. They have all sorts of nice properties, but these are the things, when people think about the standard library, this is what they think about. They think about the containers. They think about string, they think about vector. Bjarne has said, if you understand string and vector, you understand the standard library, which I think is a little overstating, but certainly you understand a lot of the containers if you just start with those 2. The second chunk is algorithms, which are a set of routines for doing various things that we're going to be talking a lot about. I'm going to be talking a lot about for the next 90 minutes. The fourth one is is utilities. There's a set of utilities in the utility classes and utility functions in the standard library for doing things like managing memory, allocators. There are things like make pair and unique pointer and shared pointer and things like that. And we'll be mentioning these as needed. There will not be very many mentions of these. And the other one is iterators. And iterators are really the glue that binds together the algorithms and the containers. We have on the order of 10 containers in the standard library. Vector, forward list, deck, 4 unordered, or 4 associated containers, 4 unordered containers. That's 12 right there. There's the containers adapters like stack and priority queue and so on. And we have some large number of algorithms. Let's just say 50. If we didn't have some way of gluing them together, we would have to have a different implementation of each algorithm for each container, each sequence. So we'd have to have a version of find that worked with lists, and a version of find that worked with vectors, and a version of find that worked with strings. And instead, with iterators, you get the opportunity to write one version of find. So you have 12 containers or whatever, 15 containers, and 50 algorithms. That's 65 chunks of code, not 750. Much better. Anyway, the whole point of iterators, you can think of them as a generalization of pointers. Basically, they are used to, well, to iterate over a sequence, to go from the beginning of an end to a sequence and return the members of this sequence. If you remember back to doing C, you had copying strings. You had a pointer to the beginning of one string, the pointer to the destination, and you just basically wrote one byte at a time from whatever the source pointer pointed to whatever the destination pointer pointed to, and then you incremented them both. We'll see something very, very similar to that using iterators. Basically, the thing that runs throughout the standard library, the basic concept of a sequence is a pair of iterators that point from the beginning of a sequence to one past the end. Most of you experienced programmers have seen this a lot, but there are probably a few people in the room for whom this is new, so I'm going to go through this reasonably quick. It's a half-open sequence. And there are different kinds of iterators. Obviously, an iterator for iterating through a list is different from an iterator going through a vector. And they have different properties. And we'll talk about those. They're kind of gathered into iterator categories. OK? We have output iterators, or iterators that you write to. And I'm just going to mention them because we'll see them a couple of times, but there's not really a lot I'm going to talk about them. But then we have iterators you read from it and you use to traverse sequences. The very first one of these are called input iterators, and they model a sequence which you can iterate over only once. You cannot back up and start over or anything like that. You can think of this as a generalization of the idea of a pointer in of a file, an open file. You can read from the file, but it's hard to go back. Or reading from a network stream, say. You read. You can't go back and say, wait, was that 10 steps ago? Because it's gone. Instead, you have to save it yourself if you want. Forward iterators are a bit more powerful. They model a multi-pass stream. You can go through the stream, and then you can go through it again and again as many times as you want. And also with, we'll just leave it at that. Bidirectional iterators, a little more powerful. You can go forward and backwards through a stream. And random access iterators are the most powerful of all in that you can not only go forward and backwards, but you're not limited to going forward and backwards one at a time. You can jump by 2s or 4s or 8s or whatever. The mental model there is you're in an array. And you can go to the fifth element easily. The way the standard says this is that random access iterators, you can advance them an arbitrary amount in constant time. You can advance forward iterators and bidirectional iterators an arbitrary amount, but it's not a constant time operation. If you think of a list, right? You want to go 5 elements in the list, what do you do? 1, 2, 3, 4, 5. If you want to do 50, 50, that's going to take a lot longer than 5. OK, so what is an STL algorithm? An STL algorithm is almost always, as a matter of fact, I can't think of any time it's not. It's a templated function that performs some useful operation, useful to somebody. Useful is obviously a subjective thing. And it's done in a generic way because you want it to be useful in more than one context. And it's not vital, but it sure helps to have a useful name. The C++ standard library is a collection of algorithms that have very generic names. They're very generic things. Things like copy and find and sort and so on. There are other collections of algorithms written to play well with the C++ standard library. Boost has an algorithms library, for example. The people at Adobe, Sean Parent et al., have a collection called the Adobe Source Library, full of interesting algorithms that they use in their products, and they've made available via an open source license. And I'm sure there are others. I just don't remember them off the tip of my tongue at the moment. So there's the C++ standard library is probably the best known collection of algorithms, but it's certainly not unique. Why would you want to use these algorithms? They're very carefully specified. They're debugged. They're tested. They're used in lots of different places, so you have at least some confidence that they are going to do what they claim to do. They're building blocks, that the algorithms in the standard library are not the be-all and end-all of something, take a collection off the net, collect a bunch of data off the network and put it in this data structure and then transmorgify it in this particular manner and then give me the top 3 of them. That is not a general algorithm. It may be a very common thing that you do in your processing, and you may want to write an algorithm that does exactly that. But the ones in the standard library do not do things like that. They can help you. They'll, for example, what I said, take the top 3. That's really a call to a routine called partial sort. And you can use that to build that algorithm that I just discussed. Anyway, they're building blocks. It's easier to write code that uses them because you can concentrate on the things that are unique to the problem you're trying to solve. It's easier to debug code using them. And boy, is it easier to review or revise later. So I have 2 chunks of code here. They're delimited by the white code at the top and the bottom of each set. The white code is identical for the 2 sets. So what does each of this code do? What each of these chunks of code do? Let's start with that. I'm sorry, I didn't hear you. Yeah, the first line creates a vector, puts a bunch of things in it. The last line prints the vector out. This one does the exact same thing, and so on. Actually, I should say, what does the code in green do? OK, several people are saying sorts a vector. So the one on the bottom, I think we can all agree, sorts the vector. Yep. The one on the top, you're correct. It sorts the vector. Every time I look at this, even though I ran this code and I tested this code and it did in fact sort the vector, I wonder if it's correct. I look at this less than equal to v size and then less than v size minus 1. And why less than equal? Why less than? Why does this start at 1 and this one at 0? And the point is that I know this code works for this example. I tried it, and I even tried it for a couple other examples. Okay, I'm reasonably confident this code works, and actually I pulled it off of a web page talking about bubble sort. This is a bubble sort implementation. So I know this code works, but I still look at it and I'm wondering, are there edge cases here it doesn't do? And so on. So the question is, the follow-on question to this, after what does this code do, is which code is easier to understand and which code is easier to reason about? Which one would you prefer to see in a code review? If somebody was written some code to go in your project and you were doing a code review on it, which one of these would you rather see? Which one do you think will be easier to extend later when you have to do something before or after the sort? Which one? This one could really use a comment that says, sort the array. OK? This one, no comment needed at all. It's very clear. I call this climbing the abstraction ladder. Basically, you're programming at a higher level. You're you're talking about what you need to do, and here, the name is really important. If this was called Fratsnabble, or Fizzbuzz, or whatever, that would not convey near as much information to you as if it was called sort. And so that's why I say, when in the last slide but one, I said, has a useful name. And there's an old joke about computer science. There are two really hard problems in computer science. Everybody know this joke, right? Cache coherency, naming things, oh yeah, and off by one errors. But the point is that naming things is a hard problem. And as you get to things that are specific to your domain, specific to your business, specific to your project, and so on, sometimes coming up with a good name is hard. And it's worth spending effort on, because you will be repaid later when you try to read the code. OK, any questions so far? Everybody happy with the idea that algorithms are, in general, a good thing to do? OK, this is about the simplest algorithm I could find. I tried writing one called identity, which is even simpler, but it's not really that useful. OK, min. This is STD min. This is implementation taken out of libc++ and then de-uglified. It's a template function on a single template on a single type. It takes two const references and returns a const reference, and it returns one of the values that you pass in. Which one? The one that's less. It compares them and returns the lesser. In this case, in the case of them being equal, it returns the second one. You can write this in different ways and ensure that it returns the first one if that's important to you. But the point is that if and again, this is just a little chunk of code. If you saw that embedded in a bunch of other code, if you saw something like that embedded in here, you would probably recognize that that was a min. But again, the name, min, you say, oh, OK, it carries additional semantic meaning. Anyway, there's also a second version of min in the standard library that takes an arbitrary comparison predicate. It takes another parameter here and uses that comparison predicate instead of less than. And you'll see that a lot in the standard library, where there's frequently two versions of a lot of algorithms. For example, sort. Sort has a 2-argument version where it takes 2 iterators and uses operator less than to order things. And it has a 3-parameter version that takes begin and end and a predicate, a function that compares 2 values and returns a Boolean, so that you can sort things in reverse order, or you can sort things that don't have an operator less than, like, say, complex. Anyway, the other thing is that this function has very, very minimal requirements on T. When you're writing your own algorithms, you want to be thinking of what kind of operations you have to do on T. It takes it by const reference, so T does not have to be copyable. We don't have to make a copy of it to pass it. And it uses only operator less than. That's the only thing it does with these variables of type T. And if you use the one that takes a predicate, it doesn't even do that. OK, I talked about copying strings earlier, and so it seems like it's reasonable to talk about STD Copy. STD Copy is a little more complicated than copying strings, but not very much. So it's a template function. Again, it takes 2 template types as template parameters. It takes 2 different iterator types, as a matter of fact. It takes 2 iterators of the first type, which I've called Iter here because that's shorter than initer or input iterator or whatever, and it makes it fit on the slide. And 1 of type OIter, which is shorter than outiter or output iterator, and basically copies the range from first to last to res or out, or I probably should have named it out. Anyway, so this and say, what would you use this for? You could use this for all sorts of things because OIter is a type. And it may be a generalization of a pointer, which means it could be a pointer, in which case you're just writing to memory, but it could be all sorts of things. The standard library has insert iterators, which insert things into a container every time you write to them. So for example, there's back insert iterator, where you say, every time you give it a container when you create the iterator, the output iterator, and every time somebody writes to that iterator, it does an insertion onto the back of the container. It adds something to the end of the container. And the containers, like vector and so on and list, will grow automatically to contain them. Another thing that you can do is you can have an iterator which every time you write something to it, it streams it to a stream. There is a stream iterator, so you can do things like copy a sequence to STD out. But anyway, the point is there's very simple here. Again, you'll see we're going to see this a lot. First, last. That defines a sequence. Okay, first, last. For nothing, first not equal to last, plus plus first. We do something with first. We're going to see that pattern a lot. Yes, somebody had a question.
At which stage it is made sure that the range of the memory pointed to by Iterator is large enough?
Okay, so the question is, at what point does it make sure that the range of memory pointed to by the output iterator is large enough? And the answer to that is it's made sure by either by the caller, if you're just giving it a pointer, or if you are if that is a concern to you, you can pass something other than a pointer here, like say a back insert iterator, which will insert items into a container, which will grow to accommodate the space. The point is that you can either assure yourself beforehand, or you can pass a smart object in as the output iterator, which will take care of that as the sequence is copied. It's not actually handled here in this routine. Okay, any questions about copy? Any other questions about copy? Sorry. Yes?
Why are first and last passed by copy?
Why are first and last passed by value and not by reference? Well, we're going to modify first. When we're all done, first is going to be equal to last. And that's not necessarily something that the caller would want. But mostly that's just a convention that is done in the standard library, that iterators are expected to be reasonably cheap to copy, and they are in general passed by value and returned by value. But yeah, the iterators that you pass to algorithms tend to get modified, and you might want to, if rather than forcing the callers to keep a copy, they just pass them by value. All right. So, yes.
Same question, but for the result iterator. What is the rationale for it to be copied? Because we're actually expecting it to be modified in some way.
Okay. Same question for the output iterator. We return it. We return the modified value, and if you want to save it back into the same variable, that's fine. If you want to ignore it and drop it on the floor, that's fine too. But yeah, in general, again, is this philosophy that iterators are a basic type that are relatively cheap to copy, and so they tend to get passed and returned by value. Okay, let's make our own. Okay, there is an algorithm in the standard library called for each, which takes a sequence and a functor, which is basically, just think of it as functor as something you can call. Okay? It could be a pointer to a procedure. It could be many things. But let's just, you can think of it as a function pointer, and you won't be far wrong. Okay? You won't be wrong for the purposes of today. And basically, it calls the functor with the parameter, which is each element in the sequence. So somebody said to me several months ago, but what I want is something like for each, but it calls the functor with each pair of elements in the sequence. So if I had a sequence which is 1, 2, 3, 4, 5, 6, it wants to get called with 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. You know, when you say each pair, it's really important to decide what do you mean by each pair. I said, fine, let's call this adjacent pair. For each adjacent pair might be a better name, but then I run into fitting things on slides and so on. So we'll just call it adjacent pair for the moment. Anyway, type name iter. We don't have 2 iterator types, we just have 1. And some functor. And we take first, last, and a functor. So let's think about this for a minute. How do we want to write it? What are some of our edge cases? First thing, all right? I described how it would work for something with like 6 elements. So what should it do if you pass it an empty sequence where empty sequence is, whoops, let's go back to here. What happens here with an empty sequence? If first is equal to last, this does nothing. It copies nothing, which is exactly what you want. If you try copy nothing to something, it's going to copy nothing and say, okay, I'm done. So for adjacent pair, if you give it an empty sequence, it should call the functor no times and return. And we're done. What about if there's only 1 element in the sequence? Sorry? Somebody said something here. Same again, yes. There are no pairs in the sequence. So there's no pairs. You can't make any pairs, so you should call the functor no times. An odd number is okay. Imagine 3. You call 1, 2, 3. You call with 1, 2, and 2, 3. Because you're not breaking it up into pairs. You're doing every adjacent pair. Yeah, if it wasn't 1, 2, 2, 3, if it was 1, 2, 3 something, then you'd have to deal with odd numbers. But instead, we're not. We're just dealing with elements next to each other in the sequence. Okay, so we've thought about that. Great. So let's just see how this would go. We say if first is not last, because if first is last, there's nothing there, and we're done. We drop a trailer to start at first, and we increment first. Now first is pointing at the second element of the sequence. And then while first is not last, we increment first, we increment the trailer, and we call the functor with the things that trailer and first point to. So let's think about this. Again, we'll just do 1, 2, 3. First points at 1, last points at just past 3. We go here, we say trailer points at 1, we increment first, it points at 2. And then we call this with 1, 2, 2, 3. And then the next time, we increment both of these, and now first is pointing at the same as last, and the condition is, and the loop condition is satisfied, and we drop out. So this is, again, this is what? 1, 2, 3, 4, 5 lines of code, 4 brackets, and a couple lines of header. I mean, this is not a big, complicated algorithm, but you can see that it does something useful. If you need, if you never need this, you'll say, that's useless. But if you need something like this, this is useful. This is You can convince yourself that this is correct. You can stick it in a library. You can write unit tests for it. And you stick it in a library, and then you just call it in your code. You say adjacent pair, or for each adjacent pair if you like that name better. And use it. And again, you get the benefits like I showed with the sort slide earlier. You get simpler code, easier to review, easier to understand. I have to admit, I did a little bit of sleight of hand here. There's a little change from for each to adjacent pair. Adjacent pair requires forward iterators. For each will work with all kinds of iterators, including input iterators. And the reason for that is because we're making multiple passes over this sequence. We have trailer and first are passing over the sequence twice. Okay? Can't do that with input iterators. If I have time, I have slides about talking about how to make this work with input iterators. But this code right here will misbehave badly if you give it input iterators. Okay, slightly different question. What if we wanted all the pairs, not just the adjacent one? And when I say all the pairs, again, you have to be careful about definitions. If you have 1, 2, 3, 4, 5, I'm thinking 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. That meaning of all the pairs, doesn't include 5, 1 and 3, 3 and things like that. So think for a minute, how would you write that? It's surprisingly similar. I call this for all pairs. Wow, consistency in naming, that's not me, at least not for this presentation. It would be better to give them, for each adjacent pair, for all pairs, so for, things like that. It would be better to name them better, but I'm pleading the necessity of fitting on slides. So here we are. We're going to do this same thing. We're going to check if the first is last, because if there are no elements, there are no pairs. We drop a trailer again, and we increment the beginning of the sequence. But then we have 2 loops here, and we say, this is the same, okay? But then we declare another iterator. From first to last, we call our functor with trailer and IT. So this trailer starts out at, say, 1 in our 1, 2, 3, 4, 5. And the first time through this, and first starts out at 2, so we're going to go 2, 3, 4, 5 for IT. Maybe should be iter, but it's already too long. And then we go, so 1, 2, 1, 3, 1, 4, 1, 5, and then we increment both first and trailer. And this is almost a recursive thing. You could turn this into a recursive solution or an iterative solution. They're functionally the same. Anyway, the point is this is not really very different from the first one. There's an extra loop here, and completely unsurprisingly, this is an order n squared algorithm, while the previous one was an order n algorithm. This obviously you're calling the functor f order n times. It's actually it's n minus 1 times. Yes.
Just a quick question: when you get a compiler error, if you try and use that without forward iteration?
Sadly, you will not. There's a way to do that using static assert. You can force the compiler errors. The question was, will you get a compiler error if you try to use this with, say, an input iterator or something? And the answer is, in general, no. Like I said, you can enforce that with static assert. And I have a technique for that at the end of the presentation when I talk about doing this with input iterators. Anyway, and obviously this requires forward iterators because we're making multiple passes over this. We're not going backwards, we're not jumping around, so obviously forward iterators is all we really need. When you're designing algorithms, you should very much think about iterator categories and what operations you need on iterators. Some algorithms require only forward iterators, like this. Find, for example, right? Real simple. Start at the beginning, look for something, go through till you find something, or you reach the end. Done. You only need forward iterators. Some algorithms, like sort, require random access because it's shuffling things all over the place, and it's looking for pivots in the middle and so on. You remember Andre's partition example yesterday in his keynote. That partition is an algorithm which requires random access iterators because it's going to jump all over the place. And if you had to, even if you had bidirectional iterators, you had to advance manually one at a time through the sequence, you would end up hurting your performance quite a bit. Sometimes, and I'll touch on this later, sometimes you can provide different implementations with different iterator categories. Anyway, more algorithms, because there's never enough algorithms. Question?
Yes, previous example, function predicate, why isn't it passed by reference?
I'm sorry, why is it passed by reference? It's passed by value.
Yeah, I mean, it isn't passed by reference.
Oh, it isn't because the original idea for this was that it was that functors would be fairly cheap. They're like you can think of function pointers. Also, you can think of STD functions. They tend to be reasonably small or small objects that have an operator, function call operator on them. If you wish to pass a functor by reference, there's this really handy utility called STDRef that's called a reference wrapper. And you just say STDRef of your functor, and it's a small object that can be passed by value, but it actually references your functor. I mean, that is exactly what STDRef is for. So if you have a stateful functor, for example, okay, something that you want to record the number of times it's called or whatever in its operator parens, then you would absolutely want to do something like STDRef of whatever. Yeah, that's the existence. The reason for existence of STDRef is to basically to let you pass things by reference instead of by value. And that way you have the best of both worlds. If you have things that can't be passed by reference because there are very few things these days that you can't pass by references, but there used to be other things. So it's your choice. By passing them by value by default, basically you push the responsibility, push the choice, I guess is a better word than responsibility, back on the caller. They can decide. Yes?
And the reference wrapper has the function call operator?
It does. The question was, does the reference wrapper have a function call operator? It does. Other questions? No, and it obviously just forwards to the thing it's referencing. Okay, more algorithms, because more. Okay. CopyWhile. This is one that actually I wrote for the Boost Algorithms library, and interestingly enough, I got the interface wrong. So copy, right? There's a whole set of things people want to do with copy. They want to do copy. They want to do, and that's in the standard library, unconditional copy, begin end. There's copy if in the standard library, which says basically copy all the values in this sequence that match some condition. And obviously you can turn that around by turning the predicate around. You can say copy if, you could implement copy if not by playing with the condition. But so there really, I don't think there is a copy if not because you just change the condition. But There's also, you can think of cases where you want to copy some stuff out of a sequence as long as a condition is true, CopyWhile, or until a condition is true, copy until, say. Anyway, there's a lot of these, and some of these were not considered originally by Alex Stepanov to be general enough to be put in the original STL proposal. CopyWhile is one of those. So what does CopyWhile do? First, last, that's the input sequence. Result, that's where the results are going to go. Some kind of predicate. The standard library tends to use the terms functor and predicate. A functor is something that, a predicate is something that takes a value or two values and returns you a Boolean that lets you decide whether or not to do something. A functor is more a user-supplied thing that does something without actually affecting the flow of control of the algorithm. So what do we do here? This part is very simple, right? For first is not last and the predicate is true for the element we're looking at, copy. Okay? So while first satisfies the predicate, copy it to result, and move on to the next element in increment first, move on to the next element into the input sequence. And as soon as you hit an element which does not satisfy the predicate, you're done. So if you have a sequence which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you pass a predicate that says less than 3, it's going to go 0, 1, 2, 3, I'm done, and return. Now, the only thing that's reasonably complicated about this is the return value. There are two pieces of information here that you want to get back out of this function. You want to get a copy of the input iterator, the iterator you were reading from, because you want to know how far in the sequence it got. Okay? And you want to return the output iterator because you've modified it. You've modified it by writing to it. And if it's representing some kind of sequence or something like that, you may want to use that as well. And so we wrap it up into a utility class from the standard library called pair. And it's a pair. A pair is a structure that has two values, first and second. And we have a utility function called makePair, which makes one of these. And once you have that, there's all the pieces you need. Like I said, there's a whole sequence of various variations on copy. There's a whole set of variations on copy that people have asked for, people have used, people have written. This is from the Boost algorithm library, and it's one of. I think we also have copy until in there, but there's not, there's not copy if not, or copy while not, or yeah. But the point is that this is, again, this is a vocabulary term. This is a name that's easy to, you see it and you have an instinctive, not instinctive. You have, just from the name, you have an understanding of what it's trying to do. And you can look at the code here and convince yourself that, yes, that's what it's doing. And then after that, when you see it in your own code base, you see CopyWhile, you say, oh, okay, I know what it's doing. And move on to looking at other places in the code for the bug, or for convincing yourself that the code is correct. Any questions about this? Okay. Let's try something a little more complicated. There are lots of different approaches to splitting a sequence based on some delimiter. And there have been many blog posts over the years. There have been articles written, all sorts of things. This was implemented in the C library. It was called StirToke. It's one of those functions that nobody really likes in the C library because it basically is not thread safe. It has this hidden global somewhere off somewhere that you better not modify. Well, how will I know if I modify it? Well, because your program won't work. Anyway. So this is a simplified one because it fits on a slide. But basically, it takes two iterators, first and last. It takes a value that we're going to use as the delimiter between the chunks of the sequence. And then it takes a functor that we're going to call with a pair of iterators that delimitates a piece of the sequence that we've split. Okay, and we're going to use a standard library function called STD find that finds a sequence in a finds a value in a sequence. And so what do? We say we're going to in my editing of these slides, I made a mistake. This should really say FW iterator, because these have in here, because these have to be forward iterators. We can't actually use input iterators here. But anyway, we find T in the sequence, okay? We look for it. Find will return the end if it doesn't find it. If it does find it, it returns an iterator that points to lowercase t. Now, we call the functor with first and found. First, up to but not including the value t, right? Say, here's a chunk. And then we set first to be the value immediately after found, skipping the t that we found, and we go around again. And also, if we didn't find it, we break. Okay, this is important because you can't actually increment an iterator past the end of the sequence, past the end value, the last value. But it's also, this is how you get out of the loop. So this is, again, a very simple program. It fits on a single slide at a not horribly small typeface. But it will split sequences based on a value. There's a couple interesting things here. The first one is technically there's no relation between the things that first points to and the value you pass in here. Somebody asked me while I was preparing this talk, shouldn't T here be some kind of thing like that? And the answer is, well, they have to be related. They don't have to be the same. They have to be comparable. For example, if you have a sequence of integers that you're looking to split, and you happen to pass something here that's a long, that's fine. You can compare ints and longs. Okay, you can even pass a double in there, and it'll get truncated. That's okay. It may be odd, but anyway. Or what's more common, right, is you have a sequence of characters like a string, and you pass an int, because characters turn into ints if you look at them funny. Single quote A, single quote, for example. Anyway, now there's lots of ways to write this. There's lots of ways to package this. Okay, and I'm not claiming that this is the be-all and end-all way to package it. This is an idea of writing it in the style of an STL algorithm. You could, in fact, instead of having a funct here, you could have an iterator that you write pairs of other iterators to, which would be a little odd, but I've seen people do them. You could take a sequence here, and actually the boost string algorithm library does that, and then you could give a sequence there that says, I want to split on any of these values. So I have a string and I want to split them on single quotes or commas or tabs, say. Or you could take a sequence here and say, I'm looking for the exact sequence, star 1, 2, 3 star, and you could work your way through it. I mean, you could do things like, you could pass in something like a regular expression here and use that as the delimiter. There's lots of ways to go here, but the structure of this kind of stays the same. You do some matching, you hand off a pair of iterators that say this is the stuff between the delimiters and so on. One of the things you notice here is if the very last element in the sequence matches t, then we will put out an empty thing at the end. We will call the functor with last, which is an empty sequence, which is exactly what you want. You want to say, if you say you have ABC bang, DEF bang, and you say, split this string along bangs, you want to see ABC, DEF, nothing. Also, if you play with this, if you go ABC bang bang, DEF, you'll get ABC, nothing, DEF. And that's really what you want, because then you can distinguish that there were two. Anyway, any questions about this? Yes, I say here first and then back there.
Is it possible to pass lambda instead of functor?
The question is it possible to pass a lambda to this functor? Yes. Now, this is a template parameter. Yes, you can pass a lambda in there. The functor here is the thing that gets called with the match. With this structure, it's not really, with this interface, I should say, because we're just matching against a single value, there's not a way to pass a lambda as a matcher, but certainly I could see writing one like this that took some kind of predicate here instead of just a single value to let you match on things that you decide at runtime. But yes, this func could be a lambda. Question in the back.
I was just wondering, would it make sense to pass last to F as well?
The question is, does it make sense to pass last to F as well? I didn't think so, or I would have written it that way, because really what you're passing is you're passing a sequence, first to one past the end, of the things between the delimiters. Certainly if you were writing one of these that your functor needed last, there's a couple ways to do this. The first one is to write this so that it passes last as well. The second one is in your functor, say as a lambda, you capture last before you pass it in. Which is better? I think that the second one would be more general, but that doesn't mean that the way you're asking for it is wrong. It depends on your circumstances. Any other questions about this? Okay. So let's talk about how you go about this. So many years ago, I read a cookbook, and somebody said a famous saying from cooks. It says, "Hunger is the best spice," and it followed up with, you should cook things that you want to eat. When you're writing algorithms, you should don't write algorithms just because, hey, I thought of this cool algorithm I should write. Write what you need, because you're much more likely to get it right because you're going to use it. Write something you need, write and use it. And that way you will get experience in using it. You will find out what it is that, you get an understanding of the problem, actually, and you will get a benefit in your code base. It should be general. I mean, if it's not that general, maybe it just needs to be a loop in some chunk of code. But it doesn't have to be universal. The ones in the standard library are very general, meant to be universal, because the standard library has to be everywhere. We hear talks about, we're writing the business logic. But mostly you're writing, when you're writing stuff to solve your problems, you're writing, I guess, domain-specific code. And there's no reason you can't have domain-specific algorithms. Boost has a graph library, and it's full of domain-specific algorithms that have to do with graph theory. Okay? They don't have to be universal. But they should be, you should think a little bit about generalizing them. Also, you can write them and use them and say, oh, that's not quite right, and improve them. This is not a write once and leave them forever. CopyWhile, for example, originally I didn't return a pair. I returned just the output iterator until somebody said, I need this input iterator because of this and this. And I said, oh, yeah, that's right. You do need that. and there's no way to get it out. So Sean Parent has been giving talks for quite a long time at various conferences about improving programming practice. And he has a guideline that he likes to talk about and then immediately gets attacked for it because everybody claims he's being absolutist, even though he says it's a guideline. It's something to strive towards, not an absolute ironclad rule. And some of you have heard that the advice that people are giving you about when you write with C++ 14 or 11, no naked news, no, use factories to allocate memory, wrap things in smart pointers so that you don't have to worry about memory leaks and stale pointers and so on. Well, Sean's thing is no naked loops. It says every time you find yourself writing a loop, okay, every time you find yourself writing a loop, Sean's advice is to think about what this loop is trying to do. Is this something that can be generalized? Is this something that can be reused? Can I stick this in a library and use it in a bunch of other places? And the answer surprisingly often is yes. But also surprisingly often the hardest thing is coming up with a name. So you want to, whenever you're writing some code, you think about, is there somewhere else in our code base, somewhere else in my professional life that I can use this? And if so, let's take a little time and make it general, and go from there. Okay. Also, it's the thing is that as you go along, as you build up a library of useful routines, it's just like we did before. You have these useful routines, but here we're calling them algorithms, right? And they can be small, like copy, okay, or they can be big, like get me such and such report. But the question is which what's the best granularity for things you can reuse? The bigger and more complicated they get, the harder they are to reuse because it gets more and more specific. In a standard library, probably sort is about as big as everything gets. There's a whole family of things around sort, like partition and nth element and partial sort and stable partition and so on. And those are all interrelated, but they're about as complicated as things get. Maybe mismatch. Anyway, so general tips about writing your own algorithms. You want to handle degenerate cases. Especially you want to handle the case of empty input. Just do nothing gracefully if that's the right thing to do. Scott Myers has written for many, many years about the erase-remove idiom when dealing with containers, because there's there's an algorithm in the standard library called remove, which surprisingly doesn't remove. Basically, you give it a range and some kind of predicate, whether it be a value or an actual function, and it shuffles all the things that match to the end. It's really partition, more or less. But anyway, it shuffles them all to the end and returns you the first element that's in that new sequence it created with the stuff at the end. And then you pass that to the container, it's called erase call, because the container manages the storage, and the container actually removes the elements from the container. Now imagine if the container's erase didn't actually handle an empty range well. Then every time you tried to do erase remove, you have to call remove and save the iterator, compare it to the end, and make sure it was not null, it was not an empty range, excuse me, and then call erase. Much easier just to have erase say, if begin and end are equal, do nothing quietly. If you give me nothing to erase, I'm going to erase nothing. Okay. Operations. When you're writing generic code, it's always important to be aware of what operations you're using on the objects that you are dealing with. If we think back to split, okay, we have to what do we have to do? We have to be able to copy. We have to be able to increment the iterators. We have to be able to compare the iterators. We have to be able to dereference the iterators. Well, we have to do whatever standard find does with them. We have to be able to copy them because we're passing them here by value. And that's about it. And whatever STD find does, and find is going to have to say, I'm going to have to compare whatever the result of dereferencing this iterator with T. Okay, that's a pretty minimal set of operations. Sort actually has a pretty minimal set of operations. You have to be able to compare. Well, you have to be able to compare the iterators, increment, they have to be random access iterators. And then you have to be able to compare the values that the iterators point to, either via less than or via predicate, depending on which way you call. And you have to be able to swap them. And that's pretty much all sort has to do. But yeah, you definitely want to be aware of the operations. The standard library has a preference for some operations over other. In particular, it likes less than. It uses less than as its default comparison operator. It uses equality comparisons. And for iterators, it much prefers pre-increment and pre-decrement to post. Because post-increment, you have to actually make a copy of the iterator, increment it, and return the copy. Which is not a big deal if you're talking about pointers, but if you're talking about iterators that are more complicated than that, then yeah, that could be a significant expense. How many people were in the pub quiz last night? How many remember problem, I think, 8 it was, that had this thing that looked like an iterator with pre-increment and post-increment, and it did all these weird things? Yeah, that looked like an iterator, and you had to think about the difference between pre and post-increment. Anyway, you should worry about complexity, because frankly, how attractive your operations are, your algorithms are, will depend on how efficient they are. You want to think about complexity, but you want to think about, actually maybe efficiency is a better word here, but mostly you're thinking about algorithmic complexity here. The for all pairs, it's an n-squared algorithm. There aren't that many n-squared algorithms in the standard library. I think mismatch or permutation are a couple, and they're not used that much. You want to think about iterator categories. And I'm going to talk about iterator categories. I apparently have enough time. But think about kinds of iterators, and you can have different implementations based on what kinds of iterators you have. STD find end, for example. But basically, you give it a sequence and another in a big sequence, a small sequence defined in a big sequence, and say, find me the last one of these. Okay? libc++, interestingly enough, has 3 different implementations of find end. If all you have is forward iterators, what should you do? You should search for the sequence. Start at the beginning, search for the sequence. Found it. Search again, found it, search again. Oh, I didn't find it. Okay, this one is the last one. Okay? There's not much else you can do with forward iterators. If you have bidirectional iterators, you can go forward and back. You start at the end of both sequences and look and look. Oh, I found it. Okay, I know this is the last because I didn't find it before. If you have random access iterators, you get an additional check. You can check things like, is the small sequence bigger than the large sequence? Okay, it doesn't exist. If, on the other hand, if it isn't, you can chop off one end of this and say, I only need to look so far. Because if I'm looking for a pattern 10 elements long, I don't have to start looking at 9 elements from the end. I know it's not there. And so we'll talk about, I have a couple slides on techniques for doing this. So I'm going to go back to, before I go on, any other questions? We're going to go back to adjacent pair. Okay, this was the adjacent pair that we wrote before. It requires forward iterators because it makes multiple passes through the sequence. It has 2 iterators that march together in lockstep. And then and calls this. So suppose you couldn't march through the sequence more than once. What can you do? Well, you can make a copy of a single element. Here we're going to save off the first element in the sequence, and then each time through the loop, we're going to call the functor, and then we're going to save off the element we just looked at, the back half of the pair. Okay, so there's a couple problems here. The first one is efficiency, right? We are effectively making a copy of all the elements of the sequence except the last one. Ouch, that could be expensive. On the other hand, you can't actually implement this algorithm with input iterators if you can't make a copy of them, so what do you do? But another interesting problem is, you gotta save this, save this. What is that thing? All you know is iterators. And it's like, what is this thing that that you get when you return an when you indirect, dereference, I guess is the better word. You dereference an iterator. Well, I talked a little about utilities way back, like the second slide. And there's this utility class in the standard library called Iterator traits. And it's a template, like everything else, and you specialize iterator traits, and you get a struct. The struct has no members in it. It has no data associated with it, but it has a bunch of type diffs in it that tell you things about the iterators. And this is really helpful because now you can write this horrible long iterator traits in iterator value type, and that's what you get when you dereference something of type in iterator. Okay, and now you have a variable of the right type to save off the element of the sequence as you march through. I had to go through this long explanation of exactly what iterator traits is because when I say it's a template meta program, people's eyes glaze over and they fall out of their chairs and they just run screaming from the room. But that's what it is. It's a function that when you specialize it on an iterator, it tells you things about the iterator. Okay, and here now we have a version of adjacent pair that works on input iterators. Single pass streams. Question in the front.
Can you not just use auto?
I'm sorry?
Can you not just use auto?
Can you not just use auto? And the answer is you cannot use auto if you're writing in C++03.
Yeah.
Okay? So you could use auto here, actually. And it would be much shorter and make it fit on the slide better. But there's another reason to use iterator traits, okay? And maybe not in this example. So the next question is, you don't want to do this all the time. The previous implementation is much more efficient. It's only if you have input iterators, if you can't use this one, because this doesn't involve copying the entire sequence, one element at a time. So if you have input iterators, you want to do this. If you have anything better than input iterators, and when I say better, it's not meant to be a value judgment, but rather there is a hierarchy of iterator classes. And so input iterator, forward iterator, bidirectional iterator, random access iterator are all related via an inheritance hierarchy. And so you want to choose this if none of the other ones will work. Okay, so how would you do that? Well, iterator traits to the rescue again. Okay, iterator traits also has a type def in there called iterator category. And these iterator categories let you know what kind of iterator it is. And those iterator categories, again, are related by inheritance. They're empty structs. They don't have any data members or anything like that. And so you can add template specializations based on that, or you can add a parameter of a particular type. And so I'm not going to show all the code because we've seen the two code. So you take these two functions and rename them, call them adjacent pair impl, say, for implementation. Okay? And you give them another parameter, forward iterator tag, input iterator tag. Okay? We're not going to use these parameters. They're empty structs. They don't carry any data. So I didn't bother naming them. And in adjacent pair, we call adjacent pair implementer first, last, f. Just take those 3 parameters, and also a default constructed iterator category. And the compiler will call one of these depending on what kind of iterator you have. And so this is how large chunks of the standard library work, this right here. You will see this is called tag dispatching. You're dispatching on the iterator category. I talked about libc++ having 3 different versions of findN. This is exactly how it works. We get the iterator category. We default construct a value of that type, empty struct. And then we have 3 of these, one that says forward iterator, one that says input iterator, one that says bidirectional iterator, one that says random access iterator. Very straightforward. The first time you do it, you'll kind of scratch your head a few times and say, huh, 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 and then you look at it and you figure out how it works, and then it just rolls off your fingers. Like I said, these are empty structs. They are very, very cheap. You know, because you can't actually have variables of 0 size, they end up being 1 byte, and a good compiler will actually not even bother passing them because they're not used. And so that's how you dispatch on iterator categories. Any questions about this? Yes?
What about pointers?
So what about pointers? So the answer is there is a specialization of iterator traits specifically for pointers. And pointers are random access iterators. They satisfy all the capabilities, all the requirements of a random access iterator. And so if you say iterator traits, pointer type, iterator category, you will get random access iterator tag. Okay. Any other questions? Yes?
What about ranges instead of first-last iterators?
Okay. So the question is, what about ranges instead of first-last iterators? Are there plans to adopt that? And the answer to that is there is a lot of work going on to adopt, instead of a pair of iterators, a range concept, a range object to model a sequence. Eric Niebler and Casey, I don't remember what Casey's last name is. Carter? Yes, thank you. And Casey Carter are working on that. It's coming along very nicely. In some ways, that's a very much nicer abstraction than a pair of iterators. And they're doing some very impressive stuff. It's not ready yet. It won't be part of C++ 17. Hopefully, whatever the next version of the standard is. If you go and look at, if you go and look on YouTube, you can find a presentation by Eric, both either C++ Now or CPPCon last year, talking about the ranges and working through an example that is surprisingly involved for what ought to be a simple problem. But I recommend that presentation highly. It's a very good presentation. And it'll give you an idea of the power of what you can do with ranges, because really he ends up with not very much code, and all of it except the last 15 lines is completely reusable in general. And so there's 15 lines to solve the problem and a lot of support code that can be reused for other projects. There are a few interesting corner cases because there are things like there are some what we call range and a half algorithms, or 3 iterator algorithms that in the standard template library where you pass a beginning and end and a position in the middle of them, and you're expected to do something based on that. And any range proposal has to take those into account. I mean, conceptually, you can say, well, those are just two ranges that happen to be butt up next to each other, and that's, I think, the way they're going with that. But still, that's a different abstraction, and some people seem to be a little, does this mean they can be apart? They don't have to be part of the same sequence when they're used to the idea of you're taking one sequence and a position in the middle and you're doing something to both halves. Okay, other questions? Yes?
Can you give some advice on testing? So if you've written like a JSON find or something in libc++, what would you do to test it?
So yeah, if I was written something like a JSON find, well, the first thing I would do, because really you have the advantage from for writing things that are in the standard, there's a definition in the standard. There's a specification. We have this 1,500-page document that specifies all this. And I would make sure that every single sentence, every single requirement that's on a JSON find has a test that tests that. And then I'd go ahead and test degenerate cases, empty sequences, things that are at the first element, things that are last element, things that aren't there, things that are in the middle. There's really no bottom to this. You have to use judgment. Test some edge cases, test some normal cases, test a few abnormal cases, but at some point you're going to say, you know what, I've got enough, and I can't give you any hard and fast answers when you have enough. I was here last year. I gave a talk called "Hardening Your Code," and there was a similar thing about writing tests. It's like you could spend a week easily writing tests for a JSON find, but 2 hours is probably enough. When I showed this to Peter Summerlad earlier this week, talking about adjacent pair, he pointed out to me that there is a function in the standard library, actually hiding in numeric, that other place where algorithms live, called adjacent difference. And what it does is, for every adjacent pair, it subtracts them, and then writes out via an output iterator, writes out the difference. And it's, you could actually write adjacent pair that I had here in terms of adjacent difference. So you just give it a slightly different output iterator, or a comparison, a different subtraction function. But I thought about that, but really, this is easier to understand. This is easier to convince yourself this is right than writing it in terms of adjacent pair or adjacent difference. Sometimes you want to build up algorithms out of other algorithms. Sean Parent has given a talk about an algorithm called gather, which I modeled on an old email program I used called Eudora. Eudora had this very cool feature that you had a list of messages, and if you option clicked on a particular message, it would bring all the messages like that together. So if you clicked on, say, the recipient column, you clicked on, say, a message from Roger, option clicked on it, it would gather all the messages from Roger together. Very nice. Or you clicked on a subject, and it would gather all the messages with the particular subject name, and and forward and so on together. Very, very useful. I have not seen an email program that does that ever since. But anyway, the point is that Sean and I were talking about this, and I had an implementation, and he thought about this for a while, and he said, you know what? That's just two calls to partition. You say right here, this is the message I want, right? And from that message to the end, you want to partition all the messages. You want to bring all the messages that match up to the beginning of the sequence. And from the beginning of the sequence down to here, you want to partition it so that all the messages that match are at the end. And now they're all together. And it's like, oh, of course. And it's like, I don't have to write, I don't have to swap things around. I don't have to worry about stability, because I'll just call stable partition, and everything will work. So frequently, you can build up algorithms from other algorithms. But sometimes, like here, using another algorithm, using adjacent difference, is probably not a good idea because it doesn't actually buy you anything either in performance or in simplicity. So it's a judgment call. Yes? Yes. And I didn't talk about that. You're correct. So what you could do here is assume that we weren't actually doing this. We weren't template. We weren't going to dispatch on the iterator type. What you could do is you can say in here, in this one, you could say static assert iterator traits bum 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 bum. Or actually, you'd have to use isSame, which is another template meta function that takes two types and tells you if they're the same type. Static assert isSame. Well, you not. Input iterator tag and iterator traits FW iterator category. So basically, you're saying, do not compile this. Give a good error message if you try to instantiate this with input iterators. And you get static assert failed. This is not an input iterator. And you can specify a message. Does not work with input iterators. You're not looking 100% convinced.
No, does a standard library do it? Does it, or is it up to the compiler to use the code in the standard library?
Oh. Yeah, it would be up to you to do this, to add this up here. You could put it right up here. It doesn't actually generate any code. It only happens at compile time. But yeah. The standard library does a mix of things. It will either rely on the compiler to say, there's some operation here that the underlying types don't support, or it just documents. It says requires forward iterators or better. Various standard libraries do various things like warn or static assert. libc++ does not enough of it. But basically, when the standard says requires such and such, it basically means that's on you. So I saw a hand here. Yes?
Just out of curiosity, is there much of a difference between these sorts of algorithms and the ones under parallel equivalence in the parallel STL?
And the parallel STL, I'm not that familiar with exactly what's in the parallel STL. We have recently adopted for C++17 the parallelism TS, which gives, sorry, I'll stand over here. Don't need to hide behind somebody, but which includes parallel versions of a bunch of the algorithms in the standard library. So there will be a parallel for each, for example, in C++17 and a parallel and various things like that. But I can't really answer your question about the parallel STL. So there's somebody over here. Maybe I answered the question. Over here.
Could you dispatch implementation on the basis of data storing inside the container?
Can you dispatch based on the type of data stored inside the container? Certainly you could. You could do it in a couple ways. The first one is you could have an implementation. You could add another template parameter here, which is some data type, and then provide specializations. And you could explicitly specialize this to be iterator, func, and then iterator traits value type, say. Because remember, we went back here. This is a name for the type that is in, well, not in the container, but in the sequence, because this could be just a pointer to an array on the heap, or even a single element that's just that's just a variable where you pass it a pointer and a pointer to one past. It doesn't actually have to be in a container. Okay. But yes, you could do that. You could specify on the type the type that the specialize on the type that the iterator points to. Other questions? Yes.
Earlier I was using standard for each a lot.
Mm-hmm.
But with C++11 and the range-based for loop, I found that it's a lot easier to use that instead of the algorithm. And I got more and more the feeling that that applies to some of the other algorithms as well. Do you have a comment on that?
So the comment was, he said he used to use for each a lot, and now he uses range-based for loops instead, and he said that that actually seems to him to be also applicable to other algorithms in the standard library. I can't speak to the other algorithms of the standard library, but certainly if you're doing something, the range-based for loop is a nice replacement for STD for each because it is just as clear. And especially before C++11, before we had lambdas, the for each was kind of awkward to use because you had to actually pass a function pointer or make a functor or something, which meant you lost a lot of the locality. You couldn't see what was going on all in one place. And the range-based for loop gets around that very nicely. The range-based for loop, interestingly enough, is in fact a call to for each underneath. I mean, it's not actually a call to for each underneath, but it is exactly equivalent to a call to for each. It packages up the thing in the for loop, and I mean, it works the same way inside. But I don't want to say that you should use one or the other. It depends on which works better for you, which you find easier to use, which you find easier to review. Going all the way back to the sort example, I would argue that you should choose the thing that makes it more understandable. And if you find you're doing the same thing that's somewhat intricate, that it's probably better to abstract that away and to call for each. If you find you're doing something that's dead simple, like printing them all out, like I did in the white code on my example, range-based for loop is fine. This is not the comment I had about Sean, no naked loops. It's something to strive for where it makes sense rather than a prescription. Don't use naked loops. No. It's a way of making your code easier to understand and also building up more capabilities for you to use in the future rather than.
Well, my question was maybe more this that some of the lower level building blocks algorithms, standard library, seem to make more sense in C++98 than they do in C++11 and newer.
Okay, so the comment was some of the low-level building blocks seem to make more sense in C++98 than they do in C++11 and newer, and I will agree to you up to a point. One of the advantages of the algorithms, as opposed to just writing your own loops, is they're composable. You can, in fact, whoops. Let me go back to split. You certainly couldn't write stdfind as a loop here, but because it really is 3 lines of code. But the thing is if all you were doing is finding something, it might, in a chunk of code and you were doing it once, it might be better to just use a for loop. But having a set of even very basic building blocks that lets you build up other things and lets you reason about them. So again, it's a judgment call.
No, but I mean, an example would be STD Copy with a back inserted to a vector, or a range-based for loop with just a putback of the vector. I mean,
I agree. You can make arguments both ways. I'm not saying you're wrong. I'm saying that again, it's a judgment call, and part of the judgment involves your audience too. If you're working with people who are who have done a lot of C++98 programming, then probably the back inserter would be ready to go. If you're working with people who are just getting started with C++ and you want to encourage them to use C++11 techniques, then the range-based for loop might be a way to go as an introduction to range-based for loops. There's not a best answer there. And we are out of time. It's 3:30. Thank you very much.